Hello, this is Mistaken Ford, and I'm going to start our video on photosynthesis and cell respiration by going over some of the major characters and plot themes that you're going to see. So much like a play that you might read in your literature class, where the beginning of the play goes over some background material, that's how I'm going to start this. And I think the reason I would do that is because there are so many common themes and plot devices, if you will, that it makes things super helpful if you understand what to look for. So these are our learning objectives for our that are in the AP course description. We're going to be looking at the photosynthetic processes and the cell respiration processes. But before we do that, we want to set the stage, so to speak. So here are the major players and plots to watch out for. The first one to notice would be electrons. Now, we know them as just, the subatomic particle that has a negative charge. But one thing that you need to understand and remember, and you learned this before in your chemistry classes, electrons orbit the nucleus in certain places called orbitals. And these orbitals would represent the amount of energy they have. So the closer they are to the nucleus, the less energy they have. The further away, the more energy they have. Now, electrons are not static. They're moving from orbital to orbital if they absorb energy. So they exist in a ground state, but they can also exist in an excited state by absorbing energy. One of the classic examples, and that's what we're going to look at with photosynthesis, if they absorb a photon of light, that electron becomes excited and it goes to a higher orbital. Now, that electron can also move from molecule to molecule, and any molecule that has that excited electron now has that little bit of energy. This is from my all-time favorite books. I taught it, gosh, back in college, and it's called The Way Things Work, and the author does a fantastic job of showing by dancers that the more excited electrons they have, the molecule will start being excited as well. And the electron can be passed from dancer to dancer and cause the dancer to start dancing. So, just like that, a molecule with that electron will also be in an excited state. So, electrons, one thing to watch out for. And in fact, so much so that I make a little goofy sign here, caution, watch for falling electrons. What you should be noticing in both photosynthesis and cell respiration is where the electron goes, that's where the energy goes. And that's what you want to keep track of. And in fact, I kind of boiled it down to three things. So, three things you should look out for. What happens to these electrons? How are they getting energized? And what can we do with this energized electron? That's going to be super helpful as we move on. What happens to them? How do they get energized? And what can we do with that energized electron? Since we're talking about electrons, what are the source of electrons? Where are they coming from? Well, one of the source of electrons that we're going to notice would be pigments. Pigment molecules like chlorophyll, or the one that we're going to look at first, Bacteriorhodopsin, they have electrons that are able to absorb a light wavelength. And we're going to use photon as the term for that little bundle of energy. And the electron in the pigments would absorb that photon. Now, when we get to cell respiration, we're going to learn that glucose would be our source of high energy electrons. But we'll get to that later. But the first thing we're going to look at would be pigments. So they're going to be our source of electrons that absorb the light. Now, the source of energy would be, in the case of photosynthesis, the light photon. When we get to cell respiration, the source of energy would be in the bonds of glucose or other carbon molecules. So electrons, and then the source of energy. Then we get into mobile electron carriers. Remember, one of my questions is what happens to those electrons? Well, these electrons get moved about a lot, and that's because we're dealing with energy, and these electrons have energy. So we want to get that energy. And so one of the other major players to watch out for would be these mobile electron carriers. Now, they look intimidating, these molecules, and in fact, their names can be pretty intimidating. Nicotinamide, adenine, dinucleotide, phosphates, flavoprotein. Don't worry about the names for now. You'll at least see them, but you should know them as NAD, H, FADH2, and NADPH. And these are the carriers when they have electrons. When they don't have electrons, they have a positive charge because they're empty. And we call them dump trucks. And I've called them dump trucks for, gosh, 2 decades as I've been teaching this. It's the easiest way to think about them. And there are all sorts of cute diagrams for them now. NADH, FADH2, and NADPH, they basically are carrying electrons. And you can see in this diagram up here, as we go from a positive to the neutral, where we carry another electron and a hydrogen. So what these guys do is they literally transport electrons. And so, just like a dump truck, they're going to take it somewhere and dump it, and then they're going to go back for more electrons. So that's another player to look for, our cast of characters. The other plots to look out for would be oxidation and reduction. Now, you guys probably learned this back in chemistry. Oxidation and reduction, there's a couple of mnemonics that you can know. Oil rig is one, or Leo the lion says grr. I like that one. So oil rig stands for oxidation, and then rig would be reduction. So oil rig, oxidation is losing electrons, reduction would be gaining electrons. So notice in our examples here, methane is going to become oxidized because the carbon loses electrons. They become further away, and that counts. Same thing when we talk about glucose. Glucose becomes oxidized because they lose electrons, they lose hydrogens as well. So oxidation is when we lose electrons, and usually that means we're also losing hydrogens. They're a pair. Every time we lose electrons, think we're losing a hydrogen. And then reduction is gaining electrons. And that's going to be the big mover shaker in terms of what's happening in our electron little play here, if you would. And then another big plot line would be electron transport systems. So right now, remember, all I'm doing is introducing you to the players and the processes that you see. So we went from electrons absorbing energy to the source of those electrons, and then I introduced the carriers of those electrons. And then what do we call it when electrons are traded? Oxidation reduction. And now we're into a system, like what's happening to the system. Now, an electron transport system is a series of proteins that have coenzymes or cofactors, and all they do is trade electrons. They alternately gain or lose. They gain, GER, Leo says GER, gain, reduction, they become reduced, or they lose electrons, they become oxidized. And we can sometimes just call it, like, it's an electron shuffle, if you will. Now, a lot of these proteins are called cytochromes. They have a heme group that has an iron in the middle. This makes them really, really willing to move electrons. They have a metal, right? That's one thing we learned about with metals. They lose and gain electrons pretty easily. And so these electron transport systems, they deal in treating electrons in a way that moves the excited electron along. And so here's a simple little graph I made where the x-axis is the path of the electron transporters. And here I've just kind of made them goofy little movers with little eyes and arms. And the y-axis would be the amount of energy that we see, free energy or energy available. And so when we have an excited electron here, usually what happens is we have an electron transport that is very willing to take it and move it along. It's very, it is not electronegative, meaning that it's willing to give its electron. And then these molecules kind of pass the electrons along. And as they do that, the energy goes down, kind of like a hot potato that gets cooler as we go. And then down here, we would have an electron acceptor that's very electronegative. It wants that electron. But now that electron has kind of spent its energy, it's done with its energy. So you're going to see these electron transport systems moving electrons along, and as they do that, they're kind of transacting energy. They're in a process of moving energy. So we're going to do these questions in class. The last major player to look for would be chemiosmosis, which is a fancy term. Think chemical and then osmosis. It's not water, but think diffusion. Chemiosmosis is when we use the power of a high concentration of hydrogen ions, and hydrogen ions are simply protons, positive charges, and we're going to use that gradient, that high concentration, to power something called ATP synthase. Now, ATP synthase has got to be one of the coolest little enzymes ever. It's an enzyme that will spin when hydrogen ions diffuse through. It's a little turbine. So protons go through, the enzyme spins, and as it spins, it exposes active sites that join ADP and phosphate to make ADP. It occurs in bacterial cell membranes. It occurs in thylakoid membranes and chloroplasts. It occurs in the inner membrane of the mitochondria. So notice in our picture here, we've got protons, hydrogen ions, on one side very high, and then on the other side very low. So usually something's driving these protons across to make a high concentration, and then the protons will diffuse through, and they're powering the production of ATP. Hydrogen ions are not turning into ATP. That's a common misconception. They're powering the ATP synthase. Much like a power plant takes the energy in water to convert to energy, we can use that ATP synthase. Here it is spinning. Here are the hydrogen ions diffusing through, and then here would be ATP coming in and joining with the phosphate to make ATP. So that would be our last player. Now, what we're going to look at in class is a very simple system that employs everything that we've talked about. So hopefully that gives you a nice introduction, and then we can kind of look at some of the complexities of these.